We are live. Okay. All right. Be mindful I'm recording right now, so I want you to give your best possible answers. What's just one thing you notice? It could be as basic as you want. One thing you notice. One thing you notice. The angle is expanding, so it starts with this initial side. You can see as theta with the green here continues around. Now we're building our theta rolling around. I like that. That's one thing. Who else has something? It can be as pure observation as that. Oh, yeah, Lincoln.
It makes hills and valleys.
It makes what?
Hills and valleys.
Hills and valleys. Nice, nice. Is there names for that in Mathematese?
Yes.
What are they called?
High points.
High points. You could say minimum, maximum, but it's really crest and trough. You guys heard that? Sonia, what else?
The red lines make a rectangle. Like if you look at the red lines that are just like perpendicular to the
I see.
X.
With this moving axis,
Yeah.
it's creating a rectangle all the way around. Wow. Wow. I'm sure there's a way to derive the change in the area compared to the theta. Beautiful. We'll leave that for calculus. Who else? Who else? Come on, there's a lot more. Good job. What else do we have? Jackson?
They're using the unit circle.
The unit circle. Everything's based on the unit circle. You could say that this is another example of the unit circle being translated into what you'll use all the time. All waves flow in this same kind of manner. With the crest, the trough. With the period is when it starts to repeat, right there. It would continue repeating this way if you kept it going. Okay. Right now we're just looking between 0 and 2 pi, you could see, but it would continue in both directions. Who else sees something? Nothing? Anyone else? Jackson.
The units on the x-axis correlate to the radian measure of the angle.
Perfect. And no matter what function we're pulling out of this, we're always going to have our x-axis, labeled at least a 2 pi, because that's one full rotation. But you could also go negative radians, right? You could change this so that theta extends here, and you have negative pi over 6, negative pi over 2, and around. That's how this will also go this way forever. It's not like the wave starts at any point. It's has no domain, or the domain's everything. Negative infinity, positive infinity. What else? Is there anything else you could see? Is there any part of this that you could stand on that you... Oh, let's go over here. Yeah, Evan. Go for it.
What were you saying?
There's one piece that's moving within the illustration that you could stand on and not fall over. Just want to give that as like an idea to look at that too. But what were you going to say, Evan?
The y value is changing with it as the x value. Depending on what x value it is, the y value at that time is the height.
Perfect. Do you have a range for us?
1 to negative 1.
1 to negative 1. Okay, so we know the range domain goes forever. Perfect. Andre, what do you have? It's okay.
But does the line connecting the point from the circle and the line on the graph is consistently growing?
It's consistent what?
Growing
And
it's level.
and its level. Good. So you can see this right here. So what you're essentially saying with that is wherever the y coordinate is on the unit circle, that's where we're finding our y coordinate as we go down. You see how they're totally synced? Right? Okay. We're going to get into all these. Any other observations? That's perfect. I like that. Gene?
The shape that the graph makes between 0 and pi is opposite but the same shape as the graph makes between pi and 2 pi.
Good. Good. It's almost like if this was the origin, that would be that x is equal to y, and it would be reflected and translated over that. So there's a reflection, and also, well, actually, there's a horizontal and a vertical translation there. Good. All right, we got like 20 things. Is that good? You want to pull out anything else? Look like you're getting one.
It looks like those water wheels. That like picks up water from the river. Yeah.
details. I like that. It could be also, imagine a train, you know, the train that has the old kind of like steam-powered train, right? You ever see like the guy walking forward and he's like standing on that bar as it rotates around? You ever seen like in the 1920s when movies had crazy things people would do? There's like somebody standing on that piece that essentially this would be the piston, right? It would be pulling it in. And as it rotates up, it would be pushing it out all the way here.
Oh, yeah, no.
You see it now?
Oh, like an elliptical.
An elliptical, good. So like an exercise machine as well?
Where you go super fast and just stand on one.
Yeah, don't do that. Or try it, be careful. Next time you're in a gym, look at the ellipticals. See if you could see the sine waves in that. If you can do that and start to see sine waves everywhere, then you understand more about like mechanical engineering. How do they make that rotate with the certain period that they need? How do they, you know, these are all questions that you'd find in engineering. So today's pretty big for like any engineering application or any science application. Because the electromagnetic waves, you would also use trig functions to devise. Don't you just like this? Doesn't it look good? It's kind of soothing. Yeah, you could breathe with that and like calm yourself down.
You should make
What should I make?
a wave trigonometry and
Okay, you do a extra credit project on that one. What were you saying about that? Same.
Basically.
Okay, cool.
I was just saying, yeah, but
Gene, what do you think?
it's too
Question: do you set out of parameters
Mhm.
by word, but those dotted lines at the top and bottom,
Yeah.
like it's not.
So I believe that those are set within this. Let's see, labels. I mean, I didn't create this. I found it. No. Sign graph.
Also, what A?
Yeah, here we go. So this is like the domain right here, and see how they made it a dashed line.
It's just for show.
So those are the range. That's the range. In here, our A is what is, I think as it's defined, our A is what is being changed. So in the sense, in this way, they are doing A is the theta value, or as it's translated here, this is the x values. So you see it in the top left. Who can tell me what function this is? Based on all the stuff we talked about, there's one hint in particular that could tell you what function this is. It's related to the 1920s, like untrained stuntman that stands on the train kind of bar that moves around. It's kind of related to that. It goes up, right? What is matching here? What is matching?
The Y.
Right? It's a straight line here because whatever the y value is around the unit circle, that's going to be our y value within our graph in this direction. It's okay. If you didn't know what it was, this is the first one we're going to start with. And it is... Yeah. It's a sine graph. It's a sine graph. The key for today is that the sine is connected to the y-coordinate. The cosine is related to the x-coordinate. So two things I want you to do. Get out a piece of paper. This is a collected classwork assignment. And also in your workbook, turn to page 149. 149 is going to have our unit circle to reference. Friday's classwork. Is that perfect? I want you to turn it all together, though. You're going to put it on the top and work.
Can I get Y?
All right, I'm going to pause it. I'm going to pause it while we do the note.
Thanks.
Not the worst. That's a joke. You know what? All right. All right, let's all look at the unit circle. You guys help me out with this. Remember that these are the radian measures. One thing that you can do, you can always access the unit circle to see what the sine values of that theta will give you. It's just the y coordinate at that theta. So at 0, let's look at this. When I'm here at 0 at my initial side, I haven't gone anywhere, right? What is my y value out here if I say I'm at 0 or 2 pi? What's going to be the point out there? 0. Is it? Think about it again.
0.
1, 0, right? It's a unit circle. 0, 0. So this is 1, 0. So I put 1, 0, but I'd remember that I'm looking at the y-coordinate for this. And the y-coordinate for theta of 0 is 0. And we'll go ahead and do for these that I'm going to point out are the special ones. We'll do it for the cosine as well. What is the cosine of 0 degrees or 0 radian? Okay. So again, it's just based on the point. This is why you won't ever have to reference this again. I'm showing you like how it's connected. Tomorrow we get into how to dissect it further. Now let's look at what's this point up here in radian? In radians? Good. Because this is pi radians as we rotate, this is pi over 2. Okay. What is my point at pi over 2? 0, 1. You see it? So I know that the sine is, the reason I put this is going to be clear later, why I did sine and cosine this way instead of switched. You'll see. You'll see. But I'm down here at pi over 2, and my y value? 1. My x value?
0.
There it is. What would we have at pi? What's my point at pi? I heard it the second time. I'm going to listen to the second thing you said. What is my sine value at pi? How do I know? I look at the ordered pair at that point. It's -1 and 0, so y is my 0. Y? -1. I think I have a way to help you remember this. That sine is the y-coordinate, cosine is the x-coordinate of theta. Why did you stop at that intersection? What'd you see? Stop sign. I've been working on that for a week.
Repeat it.
Why did you stop? Stop sign.
Like,
Sign. Why? Why sign? Man. It's like better than 5, less than 10 for sure. You're like, that's being generous. What is this radian down here? Radian here? So we have a half, we have a whole pi, so then this would be another half. Almost. 3 pi over 2. That one. And what is my point there? I don't want to lose you. Let's keep going. I mean, you could read that if you did. There's a bunch of ways to find this, even using your calculator. But here we have -1. There we have 0. Everyone agree that the measurements at 2 pi and 0 are going to match? Everyone agree. That's all the way around. You start at the beginning again. And Santoshi, question.
That's, it's really.
Guys, are we going to celebrate Pi Day?
Yeah, we're gonna celebrate Pi Day.
3.14. Yeah, but that's so far away.
I know, that's so
We
far
still
away.
got stuff?
Yeah, we have to plan it.
March 14th. We'll start planning on March 1st.
Alright, that's fine. That's fair.
It's tomorrow.
I mean, like, you just
No,
said
it's-
Pi one time, and I thought about it, and I really thought about
Just
Pi.
completely focus
Yeah.
on what you need.
It's that debate mind going everywhere.
Yeah, the attention span is
Well, your attention span is your age.
15 seconds.
In minutes.
15 years.
Oh, yeah.
That's in general
You
terms.
just stare at the
You're maxed out with your brain about 27. All right, let's bring it back in. A lot of this is exploration, so I expect some chatting. Let's keep it within the range of the lesson.
15.
All right, let's do the fourths. I want you to look on your unit circle that you're accessing, and we'll look at, let's say, what is it, pi over 4. What are my coordinate? What is my coordinate at pi over 4? You can look. Say it for me. One up. Square root of 2 over 2, and good. It's the same because it's a 45-degree angle here. If you converted that pi over 4 into degrees, it'd be 45 degrees. So we have isosceles triangle.
Isn't that like
We know this is 1.
0.86?
We know that's 1.
Isn't that like 0.86?
Yeah, the 0.86. Yeah,
Oh,
that's
that's
0.71. I want you to give it a try putting it in the fraction. We can't have a square root on the bottom of the fraction. That's going to happen when we get to tangent. We'll find that. But what I just found was pi over 4. That y is root 2 over 2. The x is also root 2 over 2. Okay. So now we're going to do like speed rounds because once we select our next theta, then we're going to find and enter that into the table really quick. I don't mind at this point if you do sine and cosine because you'll find the point. You could also, if you want, if you got this, pi over 6, you could do the sine function in radians of pi over 6. That'll give you your y term here. Right? You could then do the cosine of pi over 6. That would give you your x term. So it is also tied into just the functions on your calculator. When you get into like the practicality of how I do this, you don't need to look at the unit circle. But who wants to throw stuff in class?
We do.
We do. The collective we, the royalty. We are not amused. All right, so you're not trying for the clock. You're trying for that big box.
No, but you got it. You got it. You got it.
Confidence.
Clock is so much easier.
What? Go for it. These are speed rounds. Nice. Wow. I'm going to say that was it here?
No,
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 reason.
the top of the whiteboard here. There you go. No, yeah.
You can go again after a few.
I couldn't put clock.
No.
After class, you can stay and do that. All right, we got 3 pi over 4. Really quick. How fast can you get your x and y coordinates for that? And remember, I have it set so it's sine of x, which is our y coordinate, before the cosine of x coordinate for a reason. So when you're entering it, don't just enter it as the ordered pair. Okay, once you have it in there, raise your hand. Let's see what you got. Who hasn't done yet? Who's looking at the unit circle? Yeah, Ellie, help me out. We had 3 pi over 4.
Yes, square root of 2.
And
Negative square root of 2.
you're going to have a lot of repeats. Remember, because as you go around the circle, there's y values that are going to be the same. You're going to go up to the same part of the circle. And that's even with another point on the circle. So here we have root 2 over 2. We have negative root 2 over 2. And maybe you could see that the fourths are all going to have something in common. So who else is an expert sticky ball thrower? Gene?
So then, actually, I think Lincoln should be the next.
Yeah, Lincoln. Lincoln.
Gene, you got to go quick. Go for it. Oh, yeah, that's 5 pi over 4. Wait, did we just do that?
My life.
Do it by
my
four.
life.
Yeah. At least one was close.
All right, 5 pi over 4. This is helpful. We're going to see you went for the fourth. That's good, the quarter. You're going to see the pattern really close now.
Oh, I see it.
If you even look where it is on the unit circle and where we got these other points. 5 pi over 4, what quadrant are we talking?
3.
Quadrant 3, because pi is the border between 2 and 3. It's a little past pi. So we know this one is down here somewhere. Actually, it's exactly right there.
Fire switching X and Y. Fire switching X and Y.
Why did I put them in this order?
Is it for the tangent?
It's for the tangent. Yeah. I thought about that in the morning, but tangent gets...
That's easier.
Okay, who has this one? We're not going to do all of them. Yeah, Andre.
Oh, it's negative square root of 2 over 2.
That's the y value? No. Yeah,
Yes, the y.
and the
And
x?
then square root of 2 over 2.
That's right.
Oh, no, negative, my bad.
It would have to be negative because it's down here. Yeah. I think me questioning the first part make you question the last. All right, third quadrant. All our terms are negative, so x and y are negative. Let's go one more, maybe two. Who wants to throw it
Lincoln.
really fast?
Lincoln.
Lincoln.
I guess I'm doing it.
I guess you are from the back room.
Yes, you are.
Please do not hit.
I missed.
Yeah. That's okay.
No, wait, no, don't
I believe that was hitting the 7 pi over 4. No, we already did that one.
No, I think he was hitting 2 pi over 3.
Yeah. Wait, let's try
Wait,
again.
you
Let's
switched-
let him go again.
5 pi over 4 and
Wait,
7
but then
pi.
I gotta arc it like all of the
Yeah, we're gonna do pi over 4, pi over 3.
So much risk in that.
I know that.
Wait.
No. Let's do this. Pi over 3. We'll do that, and that's maybe where we're going to stop. Pi over 3. Go for it. How are you finding it? Are you using the calculator? Are you using unit circle? What are you doing? Okay. So pi over 3. It's about here. Well, no, it's not. It's actually upside down. And what is our point at pi over 3? Justin, what do you have?
I have square root, or for the y, it's square. Okay, x is 1/2,
Okay, that's good.
and then the y is square root of 3 over 2.
Over 2. Okay, and that's one we're kind of used to a little bit. Pi over 3 is going to be root 3 over 2. So we have 2, root 2 over 2, and root 3 over 2. That's going to be pretty common. And then we have 1/2. Okay. Everyone feel confident on being able to find the different points? Everyone feel pretty confident? Okay. So we're going to look back, and I want you to tell me what is the difference between these two graphs. So I'll give you and it's an animation graph, so it's amazing. Okay, this is the one we already saw. This is the one we already saw. Let me move this out so it's the same scale as the other. What are the things? We already noticed all the things from this, different notes on it. Okay, so we know it's really symmetric. Sine is kind of the beautiful one. Cosine is just a little more complicated. It's still beautiful. Let's see it. Ready? Oh man, it was supposed to be going. Supposed to. What am I talking about? All right, what do you think about this? What is different for this one? It's really different, right? What? Trough.
It's a graph. It's run on
Cosine graph.
I like it. Is the period the same? Is the length where it goes till it repeats the same? Pi over 0 to 2 pi. It means it's just rotating once around the circle. Okay. What's other things that are different? If the domain wasn't limited and it kept going this way, we'd see the repeat, right? We'd see the repeat. It would keep going like this. They look the same except for it's as if it's translated over like pi over 2. Okay. That's one way to think about it. What do we have? We know that the cosine theta is talking about our x-axis, our x variable. Okay, so let's look at some key points. If I go to, if I go to 0, where it's right at the initial side, right? What is my x value within this unit circle? Not connected to this grid. They kind of just put it here on its own. It's a unit circle. What is my x value there? 1. So let's look to see within the horizontal graph. Starts at 1. And it's actually, when I say it translated, I'm talking about the general shape. It looks like the sine. It would be the same kind of curvature. But it hasn't actually been translated. It's just defining now this horizontal graph based on our x values. So that's slightly different. Here, the x value, or the y value is 0. So we started at 0. Here, the x value is 1. So we started here at 1.
The x value equals the y
The...
Because it starts 1.
It does start 1 up, but this isn't the one, like when we look at the last one, it had that bar that was keeping everything like really level. That was because as it goes up with the y value along the unit circle, it also is going up on the graph. and then it goes down. It's kind of hard to do that with two hands. With this, it starts at 1, and let's see what happens. Let's observe it a little bit. Let's observe it. Okay. So notice, think about this. Well, as this little dot is going around, showing our theta, here's at 0 for x, here's at -1 for x, here's at 0 for x, here's at 1 for x. Do we see that following that exactly pretty much, right? What are our zeros? Where are our zeros where it crosses that x-axis there? Look at that. What else? 3 pi over 2. So if we look back at what we've done here, 3 pi over 2, we know we had a 0. We had a 0. The 1s are really talking about the range and the domain. Okay. You like looking at these things? I think they're kind of cool. Yeah. So let's look at, I guess I'll put it over here. I can't do that. Technical difficulties. All right. This is the cosine of theta. And we're going to go ahead and take the range and domain of this. This is going to go quick. We're going to write this down a bunch of times, so don't worry about this being part of the future notes. We're going to hit this so many times, getting the domain and range. The range is talking about my y values changing. The range is talking about the y values. The x is the domain. Jesus, I'm just writing this. Yeah, I know what. I was thinking about changing in my mind and then trying to speak it the same. The domain is talking about our x values. This is a demonstration, but we were saying that the curve would keep going this way. If we did our negative thetas, we'd be going this way. So what is my domain as far as, does it seem like there's going to be a limit if I keep going this way? What's going to happen to make it stop? Nothing. So our domain for cosine is between negative infinity and positive infinity. Okay. The range is talking about my y movement. What's the greatest y we have and the lowest y we have? 1, -1. So we're going to go -1, +1. Tomorrow we'll play with the amplitude. That's going to stretch these out so that we get higher and lower amplitude. There's some really cool stuff that happens with waves. Who's gone to the beach very much or surfs? Anybody surf? A bit? You've done it before? Okay. So sometimes what happens is, if you're in LA, there's 2 weather systems. There's one from the north and from the south. So you'll get waves coming in kind of like diagonally and kind of meeting, right? If you have a wave that is kind of low, right? But from the other direction where they're going to be able to hit each other and compound each other, we have one that goes, let's say it's like this, right? If here is kind of like, the level between the trough and the crest, it's just when the water is more smooth and flat, you would see at this point right here, it would be right here. At this point, actually I want to move this down. I want these to be a little better. What I'm trying to point out is the actual wave height, like at this point in time, would be this little portion plus this little portion. So the actual wave would be up here. It would be a little bit higher. When waves hit, if it's on the crest and crest, it makes the wave amplitude larger when you combine them. Okay. So if you're at the beach, it may seem like there's like 3-foot waves and occasionally there's like a 5-foot wave. It's because those waves coming in, they compound each other when the trough meets the trough, or when the crest meets the crest. So that's where you get really low crests and really high troughs. Low troughs, high crests. That makes sense. So that's just one dynamic. If you're going to be in engineering, a lot of this has to do with like fluid dynamics, mechanical translations of circular motion with horizontal motion. It's actually pretty, this is just a starter for you guys. It's going to go for a while. Okay, the one other thing I wanted to do, I'll let you know right now, there's no secret with this. The sign, the domain is going to be negative infinity, positive infinity, because we're translated onto the same graph here, the range is -1, +1. It's just the range. Okay. All right. The tangent is equal to the sine of x over the cosine of x. Hey, why'd you stop? Why'd you stop again? I saw the sign. That's good. Why? The sign. It's good. All right, so let's look at this. We know that it's the sine over the cosine. So watch what I'm going to do. The tangent at 0 and also at pi over 2, the tangent is 0 over 1, which equals what? 0. Let's go down here to pi over 2. We have 1 over 0. What's that equal to? Undefined. You can't say, hey, would you like one cookie? Would you like a cookie?
Yeah.
Oh, sorry, I have 0 cookies. You can have one of my 0. See, it's not even funny. It's mean. It's mean. Don't be mean. I know. If you run out of cookies, you better not offer people cookies.
What if
I ate them all.
ask Siri?
How about an end of the year, not that end of the year party with cookies?
Yay.
It should be
Wait, what do you on Friday?
Tiny cookie pies.
Tarts.
We throw pies.
I like that. What's 0 divided by -1?
You just teach her.
0. What is -1 divided by 0? No. This one over here is 0 as well. So I'm going to break this down. Hopefully I can do it without this. I'm going to see if I can position this so that I'll redraw this. I want you to see how this works. Do you remember what an asymptote is? Who can tell me what an asymptote is? It goes near the line and not touching. And why do we establish maybe a vertical asymptote? Why would we create a vertical asymptote? Too vague of a question. You need a little more? All right, how about this? Oh, I want to just point this out right here. This is a table. Dang, I have to erase this. It'll be back. You can still throw it at the clock after class.
Yeah, it was. There's no wall.
All right, let's look over here. Let's look over here. You can see that I put in, this is really the sine values in my table that you guys were making. And if I click on that, look what we get. Right? It's creating the sine curve, and we could see if we scroll down and we put the sine on top of that. See how it goes forever and we just got a small part of it? Okay. Watch this. When I interlay the cosine over it, look at that. Okay. So if you had these two waves on top of each other, like in the ocean, right here, the wave would actually be this tall. You see why? Because it's this high for the red wave, it's this high for the black wave, so we end up with a larger wave. Just want you to know that amplitudes kind of work that way. I'm trying to give you like practical ways you might visualize it. So we have the cosine, we have the sine, they're lit up here. But what about this? Let's get rid of that. Let's go with this one. The tangent. What the heck? Can somebody refine our understanding of asymptotes? Looking at the data we've already put in the table for the tangent. Can anybody refine that?
Can we see this with all three?
Next.
Okay.
Everyone's asking that. All right, you can see it. How about this? What did we have? If here's 0, what did we have for the tangent of pi over 2? Halfway around, halfway to pi. What did we have there? Pi over 2 for that tangent? Undefined. Watch what happens there. Pi over 2. Asymptote.
Oh my goodness.
What did we have for pi? For pi?
Bless you.
0. What did we have between pi and 2 pi? That's 3 pi over 2. What did we have there? Undefined. Let's look what happened. say that.
You can be mine.
Why?
How?
Stop sign.
Where? Stop sign.
It's actually easy to graph these. As you said before, the asymptote is where the function gets close to and not touched. So if I look at this portion of the tangent function, it's close to the asymptote here. I mark where my 0 is. I know it's going to continue up. As we look at the reciprocal functions, we'll see how that relates to it. But if you do that, these would all be asymptotes between this. That'd be an asymptote. Okay, so that's how we're creating the tangent function. It's harder to see this one, but we can see where the asymptotes are because it's undefined. We can see where our zeros are. There, 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 there. It's always going to be the same place for all of them. Okay. Who likes the tangent? Anybody particularly like the tangent? It's the most fun one. All right, let's see what it all looks like. Make a mental image of what you think it's all going to look like together. Boom. Boom. Let's do some more. Let's do y is equal to 1 over the sine. Whoops. Yeah, that's right. Sine of x. Watch, watch. What I just did was the cosecant and the sine. Look what happens there. The sine and cosecant are related, right? That's a reciprocal function. That's how those look together. Let's do one more. I know, right? Is equal to 1 divided by cosine of x. Oh my. So let's look. Connected with cosine of x. Oh. Connected with cosine of x. It matches that too. Right? All right, let's see what all of them look like together.
Well, you do 1 over 10.
Let's do it.
Whoa. It's just the. Yeah.
So your task for today will be plotting all the points on all graphs at the same time. Okay. You won't have to do that. Okay, it's a sign. Gene wants it. You don't have to because we haven't learned all the reciprocal functions yet. I'll take these away. Okay, let's see. What else do I want to hit? Okay, right. The one thing that's going to happen, I want you to look at this right here because we can look, if we know that the tangent is the sine over the cosine, then really all I'm doing is looking at the sine. It's root 2 over 2. And if I'm dividing by root 2 over 2, essentially, all I can do is do that flip trick for the second one. Right? Some of these are going to be really quick to figure out like that. The one that is tricky that I want to give you a heads up for is like pi over 3. Watch what happens. Root 3 over 2. It's times, or actually, that's one's fine. Where's one that we need? Somebody give me,
7 pi over 11.
No, but like one of our standards up here. 2 pi over 3. What's my point for that? 2 pi over 3. You guys looking at it? I mean, it's the unit circle. I just don't have it. So go to 2 pi over 3. Find me that point. The ordered pair there. It starts with -1 and a half. Oh, for the y. -1 and a half was for x. 2, -1 and a half. So you said it right. She was saying x first. I was ready for it. You were just making sure. Great. All right. This isn't going to happen either. When is this going to happen that I would point out? I can't pull it out right. Figure that right now. But look, if you end up with root 3 on the bottom, if you work root 3 on the bottom, we have to rationalize the expression. What's the special one we'll multiply by? Root 3. Root 3.
Isn't that just 3 pi?
It's root 3 over 3. When you multiply two rooted values, we end up with the value. There's no pi in these answers, actually. So I just want to remind you to rationalize the expression. That's mainly what we have to do. Okay, how we doing? Oh yeah, perfect. All right, we have 8 minutes to finish up your table. We still got a lot of work, but you can also, if you want to use your calculator functions, practice that for some of them. Try to make them into fractions, like so, because I want you to practice the rationalize the denominator and all that. Okay, let's get it. Thumbs up, sideways down. What do you think? Thumbs up, sideways down? It's in the middle? Okay. All right, it's a good start. Tomorrow we will bring in all the other little components. So I will say goodbye to those watching at home.
Have a good day.
Evan says, have a good day.
Yeah.
Okay.